Hi, welcome to Algomitra, your friendly guide to sizing up tricky algorithms. But today, we are not doing any algorithm. Today, I'm going to show you how we can derive the equations that predict the position of a particle under uniform acceleration and also under non-uniform acceleration, leading up almost all the way to the derivation of Taylor series. And the catch here is uh, or the silver lining here is we are not going to use any formal calculus at all. So I will just be assuming that you know algebra, a little bit of that, and you can add numbers, and maybe you know a little bit about multiplication, and that's pretty much it. So this whole attempt uh, of making this video is to kind of give an example, a proving point to someone that tries to communicate. Let's say I want to tell you something, or there is a teacher who wants to explain to students. We assume a lot of things from our audience, and it's not always necessary. You can always express your opinion in a very self-contained manner. That way you can deliver the message you want without boring down your audience or placing very high demands on them on the part of prerequisites that they have to go through. And at the same time, you don't have to be abstract or cutting out any part of the details at all. You can still build all of the concepts very thoroughly and correctly, but without relying that your audience or your students or your peers who you want to communicate with uh, know some kind of uh, abstract concepts or theory for you to be able to communicate with them. Of course, you need a common language, but then when the common language is as minimal as possible, the power for you to express your ideas to others uh, increases manifold. So, welcome. Hey guys, seen this equation? Sounds familiar, right? So, today we are going to derive it. Now, how are we going to do it? Are we going to use integration? Are we going to use differentiation? No, we are just going to use some summation and some algebra. So, are you curious to know how we can do it? If so, just continue with me and we'll work this out. Now, imagine there is a couch. Yeah, there it is, here. Let me change to my laser pointer. So, here is the couch. And what goes on a couch usually? Ah, and also a couch potato. Now, we all know that they never move. Yeah, stay at one place. Now, if you want to picture the distance between the couch here and the potato over there, maybe some point in the couch and some point in the potato, we just fix those points and then we want to measure the distance between them over a period of time. What happens? How would it look like? Yeah, it would be a flat line as below because the couch potato never moves off the couch. So it's a very easy problem to solve. So we can always say, I mean, you just put in any number here. By the way, this x-axis is the time elapsed and this y-axis is the distance between two selected points, uh, one on the couch and one on the potato. So this is just a flat line, right? So Uh, now what if we change it a little bit and then we suddenly see a tortoise. So we were just looking at the potato all the time and suddenly we saw at some instant of time we saw a tortoise pop by. And we see, okay, it's steadily going. Okay, let's see. Yeah, it's steadily going, uh, starting from the couch and then it's out of our screen now. It was moving past at a steady pace. Now if we plot the distance between the couch and the tortoise as a function of time, what would we get? Yeah, we would get a ramp like this, right? So initially the tortoise was here. As time elapsed, it was here, and then it moved there, and then it moved there and there, and then now this is just a photograph. The tortoise is out of the screen and somewhere out there. So, but how did we get this ramp? You may be wondering. I don't know, you may not be, it may be obvious, but in case you're wondering, I would try to clarify that. It's just a series of additions, right? So let's imagine that the tortoise moves 1 centimeter every second, right? So that's an easy thing to observe. Let's say we observe now it was right at the couch, then we observed it next second and it was 1 centimeter away from the couch, and we observed its position the subsequent second and it was 2 centimeters away from the couch, right? So in 3 seconds, then it would have moved 1 plus 1 plus 1 equals 3 centimeters, right? No big deal. I mean, it's a simple calculation. Now, if it was moving v meters every second, then in t seconds, it would move what? The first second, it would have moved v meters. The second, it would have moved another v meters. And the third second, it would have moved another v meters, and so forth till the tth second. So t times. So now it's a bit primitive, but this continuous addition, right? We are just incrementing the same thing over and over again. We are just accumulating, right? Now this is nothing but multiplication. So instead of writing it in this big way, v plus v n times, we have a shortcut for that. We just say t times of v. So instead of writing it this way, we just write it this way. Now that's nothing but multiplication, right? So it's just that if we have done the addition so many times, and if we have a memory of t times of v is what, then we can just plug in that value. Otherwise we'll have to add it t times. So there is no big difference. Multiplication is just a series of additions, right? And after that we throw in a bit of initial conditions and we get something like this. Let me change to something that I can draw a box around. So let's have this pen. So now this is simple, but then I want uh, you to get warmed up a little bit. So we have this basic stuff as well. So if we had a tortoise which was moving at a steady speed of v naught meters every second, and then when we spotted it first, it was like x naught meters away from, let's say, the couch or some other reference point, then the tortoise position from the couch at any arbitrary amount of time, given that it never gets tired, and if it's always moving with this velocity of v naught, then we could have it by adding up the initial position uh, together with the amount of meters it moved in t seconds, which is v naught meters in every second, and it has moved t seconds. So we have v naught t times v naught, right? So that's the basic equation of motion of a particle with uniform velocity. So yeah, so here we are representing yeah, I think we spoke of all these. So here we are just assuming that the tortoise is going on a straight track and moves only along that track, or we are only interested, we are only measuring its speed and its displacement in a given orientation, in a given direction. So after having discussed this, now look what we have here. We have a rabbit. What does rabbit do? Now, when we saw the rabbit was maybe just coming in, but then it's whizzing past us. It's not as slow as this. What's that? Tortoise. So it just whizzed past us. And if we plot, do our plot with the rabbit, what happens? We seem to get uh, we seem to get a curvy, slopy, something like this. So we are plotting we are plotting here, this is time, this 100 seconds, 200 seconds, 300 seconds, and so forth. And maybe this is the number of centimeters the rabbit has moved from the first time that we saw it here near the couch. Now this is something different. So we made these measurements, but when we try to kind of draw a line through it, we are not able to draw a straight line. So it's somewhat slopey, right? So let's see what we can do with this. With this information, can we predict the position of rabbit at any arbitrary instant of time or not? Now, so there is one thing that is sure, right? The rabbit is not moving the same number of meters every second. This is for sure, because had it moved the same number of meters every second, we would have gotten a ramp, just like how we got with the tortoise, right? The rabbit, yeah, it's not moving the same number of meters a second. Now if we look at this plot, right, so the rabbit covered in the first 100 meters, uh, in the first 100 seconds it covered 100 meters, or 10,000 centimeters. In the next 100 seconds over here, it covered 300 meters. So the first 100 meters over here, and the accumulated distance that it traveled was like 400 meters in the next 100 seconds. So if we subtract the distance it traveled in the first interval, then we get like 300 meters, which is thrice as much. And in the next 100 seconds it travels 5 times as much, and so forth. After that, 7 times and 9 times. So this is, for example, this is what we are getting by looking at some data. So we've measured the rabbit's position when after 100 seconds have elapsed, after 200 seconds have elapsed, after 300 seconds have elapsed, after 400 seconds have elapsed, and so forth. And then we say that, okay, it covered 100 meters in its first 100 seconds. After that it covered 300 meters in the next 100 seconds. After that it covered what 500 meters in the next 100 seconds, 700 meters in the next 100 seconds, and so forth. So what is going on here? What can we interpret from this? Right, it means that the rabbit is outrunning itself continuously. It's covering more and more meters in the same time interval in every subsequent uh, time interval. So the time interval here we have chosen is let's say 100 seconds. So the number of meters it is running is gradually increasing. Right? Now, we don't know how long it can do so, but it's running faster and faster than before, right? So for example, if it ran 3 meters the last second, maybe now it will run 5 meters in this present second, and then 7 meters in the next second. So what we call as speed or velocity over here, that is the number of meters that the rabbit traveled in a second, that itself is changing, right? So the data we collected from the rabbit run luckily indicates that the addition to the speed per second is a constant, right? Because we were observing this. So we had like the first 100 seconds it was 100 meters, the second 100 seconds it covered 300 meters, and so forth, and 500 and 700. So every 100-second interval it's gaining 200 meters more, right? So that is not changing. Uh, the addition to the speed that it's getting, the number of meters it can cover in a given time interval, uh, the additional number of meters it can cover in every subsequent time interval, that's remaining to be constant as per this data. So if we assume that uh, in the example that we looked at, it was always covering what 200 more meters, in every 100 seconds. So per second it was covering 2 more meters. So the same concept, if we generalize it and give it a symbol, we just say that it's covering a naught meters, a naught additional meters every subsequent second. Then uh, then the speed in every interval can be represented as v naught, and the subsequent interval would be v naught plus a naught, v naught plus 2a naught, v naught plus 3a naught, and so forth. Now if we just look at them as discrete intervals, right? So we had a very nice equation, right? We had a very simple equation which was very intuitive, uh, with the knowledge of algebra, and with the fact, with our knowledge that multiplication is nothing but a string of additions. The derivation of this formula was very simple for the tortoise. But now we know that this v naught, or the velocity itself, is not constant, and every second uh, we see there is a bump in the velocity. It's going by a factor of a naught. Now, how can we accommodate? How can we change or adapt our earlier equation that we derived for tortoise to accommodate the changes for this rabbit's what acceleration? So what we were looking at, the additional factor, what is getting added to the speed in every interval of time, uh, that in technical terms is called as acceleration, the rate at which the velocity is changing, right? So how can we do that? Now, do we need a course, because rate of changes and such, do we need a course on calculus? And now we do all this whatever dx by dt and stuff like that. F of x plus delta x minus f of x, that is like df by dx, right? And all that, continuous functions, and after that derive some uh, formulae for some differentials, and then learn about integration, know that integration is the reverse process of differentiation, forget about all this, learn all the theory, and then come back and do some substitutions, and then define acceleration a as dv by dt and such, in those abstractions. But we can do it that way, but uh, would that give us a good picture? Would that give us a lucid understanding of how we are actually uh, arriving at our derivation, or should we do it another way? So the aforementioned way of using integration and its theory, of course, I think 90% of you might have done that. So I did it too, but it always left a gap in my understanding, because there is so much of theory, and then you're taking the distillation, the gist of the theory, and after that you're doing some plug and chug to arrive at the numbers. So that doesn't really give you an understanding of what's happening physically, at least for me. So let's see how we can do it in any other way, right? So also here is a puzzle for you on which I will pause so that you will kind of try to work it out. Right? So here is the data points which we observed for our rabbit's run, where at time instant t its position was 0, at time instant 100 its position was 100 centimeters, which is 100 meters, and at time instant 200 seconds its position was 400 meters, or 400, yeah, 40,000, or 400 meters, or 400 centimeters, yeah. And that and that finally at 2500 meters at 500 seconds. Now, if this is the data that we have, can you work out what A naught is? Would it be possible to work it out? Right. It's not very difficult. So you can just pause here and try to work it out. And then when you're done, we can continue further. Yeah, I guess, welcome back. I guess you've successfully arrived at what the acceleration is for this data. Now, if you plot, now we had this plot earlier, right, where we collected the position of rabbit with respect to time. Then what if we also plot its speed? What if we plot its speed with respect to time? Now it would look something like this. So the first 100 seconds, uh, the speed is 200. After that it goes to 400, 600, 800, and 1000, 1000 centimeters per second. So it's like 2 meters, 4 meters, 6 meters, and so forth. But okay, now uh, we know the acceleration, right? Of course, you can derive it based on this, the acceleration A naught. By now, you derived it. It is changing at 2 meter each second. The 2 meters per second factor is coming into the velocity. So we know what our initial velocity is, and we know what our initial acceleration is. Now, can we define our position, or the position of the rabbit, at any arbitrary time instant, given that these conditions do not change, or till the time when these conditions do not change? Now, firstly, we plotted this velocity v rabbit as a smooth line like this, owing to our intuition, but what we have is only this data points at 100 second, at 200 second, at 300 second, at 400 second, and 500 second. But then we thought, okay, this is a nice way to join them together. But who knows, right? I mean, the rabbit could have just uh, gone back and forth and come back. So we don't know about that. So let's get real, and then instead of joining the dots this way, let's actually construct a ramp that way. So what we know is, like, for the first time instant, the rabbit's velocity was 2 meters per second. The second time instant, it was 4 meters per second, and the third time instant, it was 6 meters per second, and so forth. We don't know what happened in between. How did it get from 400 to 600? Did it get smoothly this way, or did it just jump up that way? So the more closely we observe, the better we understand. So if we observe only once every 100 seconds, we don't know that, what happened in between. Anyways, so let's divide our arbitrary time. Let's imagine we are looking at some arbitrary instant of time somewhere here, somewhere there, right? Now let's divide our arbitrary instant time t, this whole duration, into n chunks, n tiny, very tiny chunks. So we divide the whole time duration into n tiny chunks, each of having a very small width. And then let's also assume that, like how we have assumed here, let's also assume that the velocity Vn in each of the slice remains constant. Now, here with me so far, right? What do we do next? Let's make a table of the a table of the distance traveled in each of these intervals. Interval 1, interval 2, interval 3, interval 4, interval n minus 2, interval n minus 1, and add all these distances up together, then we get our x of t. So this is nothing but integration. But we don't have to just uh, shift our focus away from this problem and study some theory to do that. It's quite intuitive. Now, so here is the table. Let me erase this additional stuff here. Yeah. So we have three columns here. The first tells us the instant of time, like which slice of time we are looking at, and then the velocity in that slice of time, and the acceleration. So in the present case, the acceleration here is constant a naught all the time, so we don't have to do much calculation over there. But the velocity keeps changing. In which way? So the very first instant we have some initial velocity, let's say v naught. Over here it's 2 meters per second, let's say. And the next instant of time, what would be the velocity? Now based on the data we looked at, we already know that the next instant of time, the velocity would be v naught plus a naught into the time elapsed. And the time elapsed is delta t. We are calling it as delta t because it's a small instant of time, and usually the representation in calculus for such small amounts of anything is like a delta preceding that thing. So a small amount of time t is delta t for us. So that's the amount of calculus that we need to know. So in our instant number 1, our velocity is v naught plus a naught delta t. In the instant number 2, the velocity increases because when the instant started, its initial velocity was v naught, to which we also add in a factor of a naught delta t. And then that turns out to be v naught plus 2 times a naught delta t. And for the third one, it would be 3 times a naught delta t. And when we get to the n minus second and n minus first terms, we get v naught plus n minus 2 times a naught times delta t, and so forth. So let me erase this. So here we have all the terms. So we have all of these here. There are, how many of them do we have here? If you count them, you're starting with 0 over there and ending at n minus 1. So you have like n of these terms, n v naughts, right? And then we have n minus 1 of these terms here, where all of them have one thing in common, which is a naught delta t, right? A naught delta t, 2 times a naught delta t, 3 times a naught delta t, 4 times a naught delta t, and n minus 2 times a naught delta t, and n minus 1 times a naught delta t, and so forth. So now if we add all of them together, right? So this was how we initially thought will make the sum. I think we discussed it while we were looking at the previous slide, where we take the velocity. Okay, let me go over it one more time. So for each instant, we take the velocity in that instant and times the amount of time elapsed gives us the distance traveled in that particular instant. So V0 delta t, V1 delta t, V2 delta t, where V1, V2, Vn minus 2, Vn minus 1 represent the velocity that the particle is traveling with in uh, in one time window, in one tiny time interval, which we are calling as delta t. Now, now if we factorize a little bit and take out the common terms, we did a little bit of that when we were looking at the previous slide, right? So a naught delta t square comes out, and we have a summation here, 1 plus 2 plus 3 till n minus 1 terms, and we have v naught delta t, which goes for about n times over there. So if we know the sum of first n minus 1 natural numbers, then we are done. So we get a closed form to derive this x of t, the position of the particle. Now, do you know what this is? 1 plus 2 plus 3 dot 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 till n minus 1. I'm sure you do, but do you also know how to derive it? Maybe you do, because this one is can be done in a very easy way. So when we do the when we go beyond uniform acceleration, I think we will have to do it a little bit differently. But for the sum of first 10 natural numbers, we have a very nice trick. It's attributed to Gauss, but I don't know who came up with it, but it's very smart. So if we consider the sum of first n natural numbers as Sn, then we have Sn as 1 plus 2 plus 3 dot 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 till n. Now, all we do is write these numbers in reverse order this way. So then we also have Sn as n plus n minus 1 plus n minus 2 dot 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 till all the way down to 1. Now, if you are a programmer, you can either do for int I goes from 0 to n, or I goes from n to 0, if all you're doing is just counting, right? It doesn't matter which way you go. So if we add the first and the second lines together, we say like 2 times the sum of first and natural numbers is what? So if you add these two terms, you get an n plus 1. If you add these two terms, you get another n plus 1. If you add these two terms, you get another n plus 1. And here you have n plus 1. And here as well, you have an n plus 1. So altogether, it turns out that 2 times the sum of first natural numbers is n times n plus 1. And hence the sum of the first n natural numbers is n times n plus 1 by 2. Now if you are a programmer, this is the number of times your nested for loop will work. If you have two indices I and j, and the first one is going, I goes from 0 to n and j goes from 0 to I, then I think you get. And then if you count, if you have an accumulator and you just keep incrementing it, it will end up with this value once you're out of the loop. So now we did all of that, then we can arrive at the closed form more or less, which is here. So we have x naught, we have v naught into n times the delta t, and we have a half a naught into n times delta t whole squared, and this little other term here, right? So now we just imagine the n to be very very large, or we make more and more and more observations, right? So if we make less number of observations, maybe we don't have good enough data, but let's say the motion is uniform, and then we make so many more observations and our n is very high, then this error factor here, where we assumed our step function going that way, that would diminish to such a small extent that we could just drop this term. So because the delta t gets very low, and n times delta t is the total time elapsed t. So if we do all the substitutions, then voila, we end up with this formula. Xt is x naught plus v naught t plus half a naught t square. So, and in formal calculus, you will learn several theorems. I don't know, maybe squeeze theorem or whatever. Uh, and afterwards, to justify this, dropping this delta t term, and maybe you will also look at the binomial theorem to derive the fact that d by the derivative of any nth a polynomial is uh, n times t to the power n minus 1 and so forth. To get to this formula. But then when you use those methods and get to this formula, you actually may lose track because you have gathered all these bits and pieces of information and you have represented them as these kind of formulae. So, but how actually the particle is moving and how its velocity is getting incremented by this factor a naught here, that may go out of your mind because all you did earlier was plug and chug, whereas here we have systematically built up uh, the velocities and we have systematically calculated the distances. So I think we have a better grasp of what is happening physically. So now, taking this a little bit further, we will also consider what if the acceleration itself changes. But we will do that in our next session because we'll take a short break, and since this has extended a little bit over half an hour, uh, we'll do that in the next one, and we'll probably get to the Taylor's series as well. So hope you enjoyed this.